sense now?
Yeah.
Okay. Yes?
So I have all the information about hemostasis, but I don't exactly know what hemostasis is. It's blood
It's the
quality.
stopping of blood leaving your blood vessels or leaking out through a broken blood vessel. I should have started with that.
What does it mean when you like pop a capillary? Like,
When you pop a
you
capillary.
know, like it looks like you pop like a blood cell. You know, like it like shows up in your skin. It's like a blemish kind of, but I don't know. I just feel like people always say it's like, oh, it's pop blood vessel or like capillary.
Well, so if a blood vessel breaks and blood leaks out, then you get a bruise,
Right.
right?
Okay.
You can also get sort of extra blood vessels growing in an area, and that you can see all the little red sort of spider webby looking things. I don't know if either of those is what you're really talking about, though.
I have one on my face right here.
I think I brought that up the first lecture. Talk to your dermatologist. Yeah.
That's like if you break one in your eye, it like floods your eye.
That's right, so you can get blood that comes across, or if your sclera, the white part of your eye, gets really irritated, the blood vessels can show up in there, and those, like if you get sunburned on your eye really bad, you'll get all these extra red blood vessels in there, and it sort of shows up. So that's response to that irritation, but it's not a capillary. I'm not familiar with that phrase.
Okay.
That's sort of throwing me off.
Okay.
Anybody else have something to add to that? No.
Is that a thing? Am I crazy?
No, like,
Okay.
It's a thing.
It's a thing.
Yeah.
What exactly are spider veins then? Because they just kind of sit.
Spiders don't have veins.
Oh gosh, what is it called? I forgot what it's called specifically. But basically, it happens when usually like someone stands on their feet too long, and they basically it spreads like a spider web, and so they call them spider veins. But varicose veins. Thank you. Yeah.
Varicose vein. The veins, the walls, my understanding of that is that they get weakened and can expand. Varicose refers to a swelling. And so they can swell and the valves in those veins can fail. I think those are all contribute to it. Is anybody else a varicose vein expert who knows more about that? No. You're asking all these questions that I don't know the answer to. There's another hand that went up. Yeah.
I was just gonna comment on the pop capillary thing. Like if you play volleyball and like you get the blood spots on your arms that we're talking about.
Oh,
Yeah.
yeah.
You
Are
guys
you
all
familiar with-
volleyball players? What's the deal with that? I feel like I missed out on something.
You're not familiar with that.
What's that?
You're saying you don't know that type of.
I don't play volleyball.
They just look
It's
like
not
little
just
red.
volleyball.
They just look like little red spots.
Yeah.
They look like tiny little red dots of blood under your skin, and so that's kind of what that terminology comes from.
Ring a bell, I'm not sure.
It almost looks like
You're
just like
not.
there's just a bunch of little red dots.
All right, anything else? Just want to bring up. No. You want to ask them? Okay, here goes another one.
Well, I was just curious about bruises.
Okay.
So I understand that it's blood under the skin, but is it like a blood vessel that's going to have to really repair itself if it's like broken open, or is it a leak?
So, well, if the wall of the blood vessel breaks, then blood leaks out. Right. In most cases, you break blood vessels all the time. They're really small little breaks, and those seal up, and it's very little blood that leaks out. So it's not like you're going to get a pool, but you can have a big pool of blood, and then that blood has to get broken down. And as it gets broken down, that gives you that bruise. And as that happens, the blood vessel itself can repair itself. If the tissue just gets completely smushed and really heavily damaged, you can make new blood vessels to sort of get through that area. So that can be part of it too. It depends on how the tissue is damaged and to what extent. Anything else? We were done with that system. Okay, let's move on then to the next organ system, the respiratory system. All right, so respiration. The term respiration can be actually used in a number of different ways. And so this term is going to keep coming up. So let's go ahead and talk about different forms of respiration. So the first one, so we'll go into this in detail, ventilation. So when we talk about respiration, we can really be referring to ventilation. And ventilation is really getting air into our lungs and then back out of our lungs. Also involved with respiration would be external gas exchange. This is exchanging gases between our bodies and the outside or external environment. So think about getting oxygen from the air into our bodies, or getting carbon dioxide from our bodies out into the air. So external gas exchange. We also have gas transport. Once these gases are in our bodies, oxygen and carbon dioxide, those are the main gases we're going to pay attention to. When they're in our bodies, how do they move around in our bodies? All right, what's the mechanism for that? So we'll have to look at that in some detail. And then there's also internal gas exchange. This is exchanging gases, of carbon dioxide and oxygen. But in this case, it's all within our bodies. It's between our blood vessels and all these tissues that use and produce these gases. So it's another gas exchange, but it's completely inside the body. That's the internal part. Okay? And so these first four here, these are all components or aspects of respiration that we are going to take a look at, look in detail, see how it works. There is another part to all this, and that is cellular respiration. And really, cellular respiration is the most important. That's what all of this is for. Right? This is where we actually use oxygen and where the carbon dioxide gets produced. It's down at the cellular level. And so what do our cells use oxygen for? You guys know?
Electron transport chains.
So the electron transport chain is involved in this. What does the oxygen do for us?
Metabolism. Catabolism, right?
Catabolism. What do you say, catabolism?
Metabolism.
Metabolism. Okay, catabolism. Heard another one? ATP. Yeah, so this is all related. It's used to make lots of ATP. A lot of times people think, oh, oxygen, we're going to use the energy that's in oxygen. Well, not quite. Right? Oxygen is an important chemical in this whole process. It's involved in one of the steps, but we're not really extracting energy from it to make ATP. We'll get ATP and the energy for ATP from other things like glucose, for instance. But we need that oxygen in there, right? It's part of that electron transport chain. It's an electron acceptor. You end up making water out of that. But it's a really important molecule for this whole thing. There's this long chain of reactions that occur. And if you don't have oxygen present, then the whole system stops. And so oxygen is important for that. We can make ATP without oxygen. We don't have to have oxygen to make ATP. But we can't make enough ATP to stay alive without oxygen. So we need that oxygen to make enough ATP to keep going. So cellular respiration is really important. So important that we're not going to talk about it anymore. And you can thank me later for not going into the fine details of all that. Right? So what we're going to do is we're going to focus on 1, 2, 3, and 4 here. Okay, we're going to work our way through that and see how all that works. Here's a figure that highlights these different forms of respiration. So ventilation up here. So this little sac here is supposed to represent an air sac or all of your lungs. That's air coming in and out of your lungs. That's ventilation. Number 2, the gas exchange here. That's external gas exchange. Gases between that air space inside your alveoli. We have to talk about alveoli. Air sacs in your lungs and your blood vessels. So it's getting oxygen into your body, carbon dioxide out of your body. We've got gas transport. How are we going to get these gases transported throughout the body? It's going to be in the cardiovascular system. But how are they carried in the blood? We're going to look at that. And then there's internal gas exchange between our blood and all of these tissues or cells that use and produce the gases. And then once the oxygen is in those cells, that's where the cellular respiration will occur and where the carbon dioxide gets produced. Questions about that? No. All right. So let's look at a little outline here of how we're going to get through this system. We'll first look at the functions. What does the respiratory system do for us? we'll take just a really quick look at the anatomy. We need to be familiar with some of the parts so that we can talk about how it all works. So we will look at that. Then we'll go ahead and look at the mechanics, right? Really the mechanics of ventilation. How are we going to get air in and out of our lungs? We'll look at gas exchange, both external and internal gas exchange, and gas transport, how we move those gases around in our blood. Okay, so it's the different forms of respiration, but we'll start with the overall functions of the system and the anatomy. Okay? All right, what are the functions? Well, for one, it's gas exchange. This is what probably comes to mind first for most people. One of the main jobs of the respiratory system is to exchange gases with the outside environment. Again, the main ones that we're going to be worried about, oxygen and carbon dioxide. Right, we need to gain oxygen, and we need to get rid of carbon dioxide. Right, there are other gases involved as well, for instance nitrogen. Right, that's the more common gas. So that's going to be coming in and out as well. We don't have to pay as much attention to it because to a large extent it's sort of inert. It does have some function, does some things, but we're going to concentrate on oxygen and carbon dioxide. Another really important part of the respiratory system is pH balance. Right, helping to control how acidic or basic our bodies are. Which at first seems a little bit weird, right? Because we're not breathing acid, right? If we're too acidic, we don't exhale a bunch of acid out into the air. So what is the connection there? We're going to take a closer look at this when we get to the renal system. But just for now, to sort of give you something to chew on with that. Carbon dioxide, when it mixes with water, it combines to form an acid. And so when we're exhaling carbon dioxide, that's directly relating to the amount of acid that's in our bodies or really available in our bodies. So that's the connection between pH balance and respiration. What else? Protection. Right? So there are a number of sort of mechanisms with the respiratory system that protect us from things that could damage our lungs, for instance. Let's think about when we're breathing air in. That air is not clean, right? Especially if we're in a city, right? There's all kinds of gunk in the air that we don't want in our lungs. Our lungs are extremely fragile. The tiniest particles can easily rip our lungs, and so we don't want extra stuff in our air. So we have a number of mechanisms that will help prevent some of those particles from getting in our lungs. For instance, nose hairs. Right? When you inhale through your nose, those hairs can trap a number of particles. Right? There's mucus lining your nasal cavity. So as that air comes in, particles can stick to that mucus. In fact, that mucus goes all the way down to your lungs. And so you can trap particles all the way down, keep them from actually getting into your lungs. And then we've got cilia in most of those parts that will actually create these mucus currents to get that to flow away from your lungs. And then you end up either swallowing it or spitting it out. All right, so a number of ways to protect our lungs. And then the last one on my list here, vocalizations. All right, so our sound production starts with our respiratory system. By forcefully pushing air out of our lungs, right, that air flows past two little folds of tissue that we can adjust how far apart they are and how tight they are, and that controls how they vibrate. And those vibrations produce sound. And then as that sound resonates in our oral cavity and the sinuses in our head, it creates all these different noises that we can make from our mouth. Right? It allows us to talk. So our respiratory system is pretty important for that as well. Questions about these functions in general? No. All right. Let's go ahead and take a look at the anatomy. So we've got some parts to work with here. All right, so most all of this is in the thoracic cavity. A lot of it is. Thoracic cavity is going to go from your diaphragm, that's that sheet or dome-like muscle, it sits right on top of your liver and your stomach. So thoracic cavity goes from that muscle all the way up to the bottom of your neck. So in there are some bones that we need to pay attention to, primarily our ribs and our vertebrae. I guess I could put on this list also sternum. So our ribs attaching to vertebrae posteriorly, sternum anteriorly, all that together creates this rib cage, right? And all these ribs are going to be really important in how our respiratory system functions, especially ventilation. Right, we're going to see that it's really important in allowing our lungs to fill up and get air out. There are a number of muscles that are involved as well. And to breathe is an active process. It takes energy. You have to contract muscles to do this. And so that will involve the diaphragm I just mentioned. It's that dome-like muscle right underneath your lungs, on top of your liver. And then another set of muscles, the intercostal muscles. Intercostal. So the name tells you where these are. Costal refers to what? Your ribs, and inter means? Between. So between your ribs, you've got muscles in there. So when if you're one that eats these things, if you eat ribs like, pork ribs or beef ribs or whatever, you're eating intercostal muscles. I wouldn't recommend ordering that way at a restaurant. Who knows what you'll get? But that's what you get. All right, so in this drawing here, we can see some of the bones, the ribs here that are joining up with the sternum in the middle. You can see sort of underneath those ribs, that's the diaphragm, that dome-like muscle. Your lungs will be sitting on top of that. And between the ribs, we have the intercostal muscles. There are actually two layers. There's an external intercostal muscle and an internal intercostal muscle. So both of those are going to be important. All right, what else do we have? We talked about bones and muscles. There are also some sacs that are real important, right? These membranes. These membranes. And these membranes that we're going to talk about surround your lungs. These are the pleural membranes. Each lung has this membrane wrapped around it. Go ahead and look at the diagram. So here we've got our lungs, and if we made a slice through our lungs and look straight down on it, we could see, they added some things in this figure, you can see a vertebrae in the back, you can see some ribs, we've got our lungs, a heart sort of sandwiched right between, esophagus, that's part of the digestive system. But notice each lung has this dark blue around it. That's representing these pleural sacs or pleural membranes. So each lung has this membrane surrounding it. And these membranes, let's take a closer look at them. All right, so the pleural sacs are made up of these membranes. These membranes have two layers to them. So you've got your lung, and then one layer that's stuck to your lung, and then there's a little gap, and then another layer outside of that. So there's two layers to it. That outer layer is actually stuck to the inside of your thoracic cavity. So you've got one layer stuck to the inside of your ribs, for instance, and then the other layer stuck to your lungs, with this thin space between the two that's filled with pleural fluid. So this membrane is a double-layered or double-walled membrane. If you've heard of serous membranes, this is one of your serous membranes.
So the inner layer stuck to the lung?
Yes. Yeah, so one layer stuck to your lungs, the other one stuck to the inside of your thoracic cavity. These two layers, though, are actually continuous with each other. So you've got this outer layer, and then it curves around and starts to form the inner layer. Let's look at a sort of simplified drawing to get an idea about this. So down here we've got our lungs. The blue all around it represents the pleural sacs. And you can see this dark blue, the inner layer stuck to the lung, is actually continuous with the outer layer that's stuck to the thoracic cavity wall. To get an idea, visualize this. Imagine that you had, let's say my left fist is an organ like your lung, and then in my right hand I've got a balloon. Let's say it's a water balloon, but it's not filled up too much. Right? It's tied off. If I take my lung or my fist and I slowly push it into the side of the balloon, part of that balloon comes in direct contact with my fist. That's the inner layer. And as I keep pushing it in, we also have the outer layer that starts to wrap around my fist. And that's what we see over here. All right, so that inner layer stuck to your fist or stuck to your lung, then there's that outer layer. And between the two is the water that was in the balloon. Okay, that's that pleural fluid that's in there. Everybody feel good about the pleural sacs? All right. So whoop-de-doo, what do these things do for us? Well, they have a couple jobs. Right, this kind of membranes found in a number of different places in your body. And for the most part, these membranes, what they do for you is they reduce friction. So all day long, your lungs are getting bigger and smaller, and they're moving around. And in between your two lungs, you've got your heart, and it's doing its thing all day long also. It happens to have its own double-layered membrane surrounding it, but you've got all this stuff moving around in there. If your lungs and your heart did not have these membranes around them, then they'd be right up against each other. And then your heart would be rubbing up against your lungs, and your lungs up against your heart, and it'd be a big mess because you'd start to wear holes in your lungs and in the side of your heart. That would be a problem. Right? And so what this does is it reduces friction. The two layers easily glide relative to each other. Right? They glide relative to each other, so it dramatically reduces friction. The other big benefit, specifically for the lungs, is that it prevents the lungs from collapsing. We now know from the respiratory lab that you can't get all the air out of your lungs if you're going to still keep everything intact. Right? You exhale as much as you possibly can. There's still air in your lungs. Your lungs do not collapse. If they did collapse, you wouldn't be able to take your next breath. And when we get into the details of ventilation, how you inhale and exhale, that'll become more obvious. But these membranes allow your lungs to stay with the wall of your thoracic cavity. So when your thoracic cavity wall moves, your lungs are going to move with it. And why is that? Well, we've got those two layers to the membrane, and in between the two is a thin layer of fluid. So they glide relative to each other very easily, but they don't separate or pull apart. So imagine you've got a microscope slide, this glass slide, and it's wet. You stick it down on a counter. If you do that, can you easily pick the slide straight up?
No.
No, you can't. Right? Unless you pump a bunch of water underneath and then the thing's just kind of floating. But if it's just a real thin layer of water, it's stuck. You can't just pick it up. You can slide it on the table very easily, but you can't just pick it up. And that has to do with the way those water molecules are interacting with each other in the table and the glass. Same thing's happening with these layers to the membrane. Those layers do not separate from each other. If you move one layer, the other one's going to move with it. They can glide relative to each other, but they don't pull apart. And that's what keeps our lungs filling the thoracic cavity. Everybody feel good about that? Yes.
Is it made out of smooth muscle or skeleton?
These membranes?
Yeah.
It's made out of epithelial tissue. It's an epithelial membrane, so there's also connective tissue in here. Anything else? Yeah.
So, I had a friend who landed on their back and they called it like a lung collapsing. Is that when the pleural sac will burst?
So usually it's not that it bursts. I mean, you can rip through it. That's a problem too. But your lung can actually separate from, or one half of the membrane separate from the other half, or have your lung pull away from the thoracic cavity wall. That can happen, and when that does, that part of the lung collapses. So your lungs have multiple lobes to them, and so they don't necessarily completely collapse, luckily, right? It's usually just a partial collapse, and you can kind of breathe. You're not going to go run a marathon, probably, but you can stay alive. So that might have been what happened, that your buddy just got jarred so hard that it somehow pulled it off. Or if a rib broke, a lot of times that can help it separate as well. Is there another question here?
No.
Just play with your pen. Did you have a question?
Once it separates, it can never fuse back together.
So it can. So there are different techniques to try and get it to reattach. I don't know that they generally do on their own, but there are ways to sort of suck the air out or push the lungs out to it to have it sort of realign. And once it's stuck back out there, then hopefully you're good to go, assuming that there's no hole all the way through. If there's a hole, then that screws it up. You gotta get the hole fixed too. Okay, anything else? All right. We're going to talk about this. You guys done with pleural membranes? Yes, move on to something else. Okay, let's just run through the airways real quick. Just so everyone's got it sort of fresh in their mind, the path that air is going to take when it goes into your lungs, and then keep in mind it's going to go right back out the same way. So we'll go follow a unit of air during inhaling. All right, so we start at the nose. Right? So when you first start inhaling, air comes in through the nasal cavity. Yeah, you could inhale through your oral cavity, through your mouth. Right? That works. You can still get plenty of air that way. In fact, you can get more air that way. But you miss out on some things. Right? So what do you miss out on? Well, I already mentioned this before. You miss out on the opportunity to filter your air to some extent. You don't have those nose hairs. Right? You don't have hairs lining the inside of your mouth. Well, that would be weird. I don't really want to think about that anymore. So that, and then also your nasal cavity has a very large surface area for the volume that's in there. Right? So sure, there's a big pocket in the front that you could stick your finger, but you're not supposed to. But behind that, right, is a very small space. There's lots of surface area in there. And that's all aligned with a mucous membrane. Right? It's real wet in there. So any air that comes in through your nasal cavity is going to come in really close proximity to a mucous membrane where it can trap and capture some of these particles that are in the air. So it's really going to help to filter that stuff out. It also really helps with humidifying the air. Right? Because the nasal cavity is lined with water, it's got that really high surface area to volume ratio, the air that comes in contact, really close contact with water. So it makes that air really humid, which is going to be really important. If oxygen is going to make its way from our lungs into our body, it first has to dissolve in water. So you want to make sure that air is really wet. Evidence that this air is very wet is exhale on a cold day. Right? When you can see your breath. Well, you don't really see your breath, but you're seeing one part of it. Right? You're seeing the water vapor that's condensing in this cooler air. Right? Cooler air holds less water vapor than warm air. It's pretty warm and toasty in your lungs. When you exhale, that air cools fast, and it can't hold as much of that water vapor, so some of that water vapor condenses and you form a little cloud in front of you. Okay. What else does it do for you? It helps to heat up that air. Right? You want to make sure that that air, when it gets down to your lungs, is at the same temperature as your body temperature. Because that's going to help influence how much oxygen and carbon dioxide the air can hold. And so when you inhale through your nose, and that air goes in, the blood vessels that go through that mucous membrane, for the most part, are oriented from back to front. That relatively cool air comes in, and now you've got this gradient. And that's a really efficient way to exchange heat. So heat from your warm blood gets transferred to that air that's coming in to heat up that air. So that's a countercurrent heat exchange. You don't have to worry too much about how that works right now, but when we get to the renal system, we're going to talk about countercurrent systems. They'll come up again. So it's actually in a lot of different places throughout our body. It's a really important mechanism, but we'll get to the details of that when we get to the kidneys. So by breathing into your nose, that can help heat up the air. If it's really cold outside, right, and you slowly breathe in through your nose, everything works fine. But if you really fast inhale through your mouth, right, it can hurt your lungs, all that cold air rushing in. You can feel the difference in the temperature of that air. Right? Okay. You done with the nose? Almost.
I'm just thinking about like when people run, they tell you to breathe through your nose and out through your mouth. Is that for respiration reasons or just to control our breathing?
Well, I know a benefit of that is you get to filter, humidify, and heat the air. If that's what the sports coach is trying to go for, I'm not sure. I don't know if there's some sort of sport performance benefit to that. Does anybody know? No comment on that. Right? You can increase the volume of airflow through your lungs if you go in through your mouth, because there's less resistance to flow through your mouth versus your nose. But you do miss out on those other benefits. Okay, anything else? All right. So once air comes in through the nasal cavity, it goes down the pharynx. The pharynx is this space behind the nasal cavity, behind the oral cavity, and it goes down to the next part, the larynx. You can think of that pharynx as sort of the back of your throat. We'll come back to that and talk more about the pharynx when we get to the digestive system. Because part of that pharynx is a shared structure with the respiratory and digestive systems. All right, so the larynx. So the larynx is a real important part. right at the beginning of the larynx is where you sort of decide which way are you going to go, right? Is whatever coming in going to go into the digestive system, or is it going to go on into the respiratory system? If it goes into the digestive system, at that point you'd go down the esophagus to the stomach. Right? And so if you swallowed air, right, down in that direction, is that a big problem? Big problem? Why is that a problem?
Did you get hiccup?
You don't necessarily get hiccups.
Well, if somebody's unconscious and they get a bunch of air into their stomach, they might throw up.
So they might throw up, and throwing up could be a problem. My kids think it's hilarious, because then they get to burp, right? Because you got to get the air back out. All right, so if you swallow, let's say you do it consciously and control and just a small amount of air, then you got this pocket of air in there, and then you can go ahead and push it back out, and it burps, and you can make a funny noise, and everyone laughs. And I have to pretend like that's not appropriate. I'm really laughing on the inside. But if you went the other way, you go down the larynx towards the lungs. Right? So that's where we want our air to go. Let's say food goes in that direction. Is that a problem? Yeah, that is a problem. What's the problem with that? It's choked, right? So it can block your airway so you can't get air down in there. Right? So that's a problem. All right. So once you go through the larynx, then you enter into the trachea. Some people call this the windpipe. The trachea is this tube. It's got these cartilaginous rings in it to make sure that it stays open. Right? So we'll see when we get to ventilation that we end up sucking air through this tube. If you didn't have those cartilaginous rings in it, that tube would collapse when you tried to suck air through it. So it's like sucking on a weak or a thin-walled straw. Right? Like imagine you're going to suck on a McDonald's straw to get a milkshake through it. It doesn't work, right? The straw collapses and then your head kind of wants to burst because you're pulling so hard. Right? So to prevent that, in our trachea, we've got these cartilaginous rings, so it stiffens it up, keeps that, that tube open so air can get sucked through it without it collapsing. So that's our trachea. Then the trachea splits into two primary bronchi. One goes to the left lung, one goes to the right lung. So the primary bronchi. And then those bronchi split into secondary, tertiary bronchi, so smaller and smaller bronchi, as they branch to go throughout the lungs. So your lungs have all these little tubes going through them. Right? Your lungs, each lung is not just one big